All right, as we discussed last time, impulse or the change in momentum is how the force applied for a period of time affects an individual object. So this is the reason why an object would change its motion, right? In Newton's laws, we would say that that is the reason why it overcomes the first law, the law of inertia. So the object's momentum changes as an applied force acts, or an impulse. However, if we define a closed system, a system that does not interact with the environment, then momentum is conserved. And we use this in isolated systems to define the motion characteristics of objects within that system. Even if their individual momentums are changing, the system as a whole maintains one consistent value. Notation-wise, we think of it like this: P equals P prime. Now, it's true that we do use the prime notation in calculus to define derivatives, but here we are simply describing the momentum of the system before equal to the momentum of the system after. Right, but it's important to note that this is the system's momentum, and this is the momentum of the system after whatever interaction happens at this equal sign, not the individual objects within that defined closed system. The most typical examples are collisions between objects that we define within that given system. So collisions are a very common practice for momentum conservation. There are two basic defined collisions. One is a bouncing scenario, and one is a sticking scenario. These are often mislabeled as elastic and inelastic, depending on which textbook you are reading. And it's an unfortunate reality because, by definition, an elastic collision is said to maintain perfect energy balance, or in other words, there is absolutely no loss in energy. So this would be an ideal situation. So the reality is that in the real world, bouncing and sticking are actually both inelastic, where energy is lost into the system in the form of heat, sound, light, etc. For simplification purposes, this is often what's used, but the reality is that the two scenarios are bouncing and sticking, and elastic is just simply an ideal situation where no energy would be lost. Like I said, these things will not actually be perfect collisions where they don't lose energy, but we will look at them in some cases where we're essentially pretending that it's a perfect situation or an ideal situation. When objects collide, we are simply going to define the system, whatever that closed system may be, and then assume within that system that there is no interaction to the outside world, right? And so the most basic example is billiard balls, where we have something like ball 1 moving forward and colliding into ball 2, which is stationary. And then after the collision, we have ball 1 reacting in some way, and then we have ball 2 reacting in some way. And so in some cases, we would expect that ball 1 would come to a stop, but that's just simply an assumption. We don't know that for sure, and in any given real-world situation, it could absolutely be that this one continues forward slower, or happens to rebound backward, or even goes off in an askew direction with multiple dimensions. Each one of those cases will be different. We will explore that further when we get there.